So we can quickly come back. So welcome again to the AI class. Last time we were stopping like when we were talking about the propositional logic, and within the propositional logic, we were discussing a very important like concept, which is the proof by resolution. The idea of proof by resolution is that given like a fact, in order to prove that is correct, we can prove the opposite. Means we are going to apply a contradiction and then we conclude if this is true or false. Now, in order to do so, we went through very basic like definitions of a clause, of conjunctive normal form, which is the CNF form, and we have said that the CNF is just a logical sentence that is a conjunction of clauses, and in this case, what we were saying, like a set of boxes, these boxes like A or B or C, where we have the or, and these boxes are connected or conjuncted via the and symbol. So in order to do like, or in order to prove to make this proof by resolution, what we need to do is, the first thing is, given a sentence, we need to write that in the conjunctive normal form, and that happens by eliminating like things like the biconditional, the implies, and so on, to have like just boxes, like I was saying, connected via an and. We can find the or for sure inside and the not if it's there. Next, we apply the resolution inference rule to cancel out complementary letters, and we were saying that these are if I have an event and the opposite of that event, the negation, or I have, for example, B11, so I have, in the other hand, not B11. So both like elements we can eliminate and or not consider. First step, so how to convert to the CNF? We have in this slide a set of rules in order to eliminate the biconditional, in order to eliminate the implies, the not, and to apply the distributivity law. First of all, for eliminating the biconditional, we have P biconditional Q. It is exactly equivalent of going from P to Q, means P implies Q, and at the same time coming back in the opposite direction to go from Q to P, which is Q implies P. We eliminate the implies itself also by having the rule that P implies Q is equivalent to not P or Q. And we move the not inward and apply the distributivity law like we were seeing last time. Next, we apply the resolution inference rule. So as this is just a notation, we have on the top P or Q. This is our given facts, the first one, and this comma. The other fact is not P. So from this, we are going to prove Q, and this is just a notation. For example, here, we have an example of full resolution inference. On the top, I found my given facts, which are P1 to PQ, like an OR, and an OR connecting Q1 to Qn. Starting from here, I am going to prove this, okay? So this is an example of the notation. Now let's go through the proof, through thoughts, like through the truth table. And if we have now, at the one hand, our like given, what is this? P or Q. We call it facts. This is what we have in hands. And at the same time, we have not P or R. So this is what we know. P or Q, it is taking the value true, for example. And the other one, which is not P or R, is also taken true. So if, for example, now we know that P is true, P could take two values, whether true or false. Given the particular case where P is true, how could we evaluate the Q or R? This is the final evaluation, and both Q and R can take like values based on the given information.
It must be true.
True. True. So if R is true, then it is true. And given that P is false now. Q is true. and so the only here we are only varying P. One time P is true, one time P is false. So what I have, P or Q, it's true, and this element which is true, and given that here I know that P is true and not P is false. So here I will take the case that P is true and P is false. So if I need just to reason about this Q or R. If Q or R, when Q or R could be true, it could be true if R is true or if I have Q is true. Okay? Clear? Okay. So now we can do the same thing, not through the truth table, but through the chain rule. We did this before or not? Okay. So if we are going to do this through the chain rule, what we are going to write this like facts that we have. We have the comma here is translated with an and. So I have this, and through the chain of rule, I need to come up to Q or R, or the opposite, not Q or R, which is the opposite. So we need to start. I have P or Q and not P or R. So this is equivalent to not Q implies P, and I also can write this as P implies R. So from this, by the chain of rule, I will be having not Q implies R, because I have something that's taking me to P, and at the same time from that P I'm going to something else. So that something is taking me to R, which is the chain of rules, and then this is yes. So we are proving that. Is that clear? Yes. Okay, that's great. Now, if we have the inference by resolution, we know just to have, as I was mentioning, a given fact, for example, P or Q, and if I have, in the other hand, here it's like an and, okay? I have not P or R. What can we do in this case? Or what can you remark in this case? We have, at the same time, P or Q, and here we have not P. So if we have P and not P, it's like contradiction. So what we can do, this is exactly equivalent to eliminating that P and having Q or R. Is that clear? Online?
Yep.
Great. So the next example now, for example, we have P or Q or S, and then we have means and, not P or R or S. So in this case, what you can see, P and not P is like complementary. So what we will have, Q or S or R or S. So what you can hear? Redundancy, you are right. So you can see the S twice. As we have an R here, so we can remove that S, only like one is enough. Is that clear? So these are the main key. So if we have P and not P now, we don't have anything else connecting them. I have P and not P. So what will be the result in this case?
Nothing.
Nothing means what? Yeah, so it means an empty list, for example. Okay. Now we can go through this like resolution algorithm if we want to see it, how this could be like written as an algorithm. So what we have in hands is the knowledge base, KB. We aim to now alpha. We have alpha KB. So implies alpha is equivalent to not KB or alpha. So this is what we need to prove. We will go through the proof by contradiction, which gives that KB and not alpha is unsatisfiable. Okay? So the algorithm is given as follows. We define a function, which is the proof by resolution, for example. It takes as input both KB and alpha, and based on that, it will return a Boolean-like result, whether true or false. Our inputs, KB is the knowledge base, a sentence in propositional logic. Alpha is the query, which is a sentence also in propositional logic. And the set of clauses represents the set of clauses in the CNF representation of KB and not alpha. This is what we are going to reach, and we initialize our new, we are going to store the results there as empty like list, and we have like usual a loop. Now within the loop we have for each like element. What we will do, we are going to apply the resolution inference rule. Okay, so the resolution inference rule, we were already going through this, and this is going to be as like a recursion. Okay, and then we are each time, if for our resolvents contains the empty clause, then we return true, and each time we add to the list, it's the union. Otherwise, it is going to have as a subset the different clauses, then return false, to have it like again the union with the new elements. Okay, now let's take an example to make a concrete example. So what we have in our KB, we have B11. You guys are now familiar with the B and P notations and still remember that or not yet? What is B and what is P?
Breeze and pit.
Yes, so at least great. So if you guys still, we are in the same example of the Wampus word, and we have B11 means at the in position 11 we have breeze. P12, for example, there is like a pit in 1, 2 or a pit in 2, 1. So this is the example we are still working on. So this is our KB. On the one hand, we have B11 biconditional P12 or the P21. And so this is the example. If you are, so we have our grid, and in the first like room, let's say, we have our AI agent is here, and so this is the B11, and the idea is that there is a pit whether in like 2, 1 or in 1, 1. Okay, so we need to prove now that it is equivalent. How? So we need to go first of all, we have B11 and not B11, and our alpha in this case is not P in 1, 2. Okay, so how to do so? We have our knowledge base here. We have both like KB and not alpha. This is what we were saying we will do. And KB, it's not B11 or sorry, P12 or P12. And at the same time, we have not P12 or B11 and not P21 or B11 and not B11 and P12. So what is this long expression you see over here? Yeah, you are right. Okay, so we are moving to write this like facts that we have in a form that we do not have this implies. Okay, so this is the CNF form of all of that. How to present that now? We are, as I was mentioning, I said each element could be seen as a box, right? So you can see your here. For example, we start from the atomic expression P12. This is a little box, okay? We will represent it like this, P12. Then I have my not B11. I'm going to mention here. Then I have not P21 and B11. And so on. So I am presenting my set of boxes. And each time I am going to check where that takes me, okay? Until I am finding that I can prove the opposite of my expression. And so I can say that it's like solved. This is what we need to do. Is that clear? Okay, that's great. Now the main advantage of all this, so that is, it is declarative, which means we have pieces of syntax that correspond to facts, and that's clear, okay? It is compositional and allow practical, disjunctive, or negated information, unlike most data structures and database. So this is another strength point. And the meaning is context independent, unlike natural language. Because when we see last time an example of natural language, like I think it was I love you, that example, and we say, for example, the like word that is giving the whole like meaning of this is the verb, which is love. However, this like verb depends from I and you. It's putting this relationship. So I cannot, it's okay. I can extract like a piece of information that summarizes the whole thing, for example, but I cannot stay independent from my context. So in this case, we can stay independent from this context, but the only limitation that I may mention is that this is a very limited expressive power, which means if I can say I love you in this, for example, in the natural language, but this is very simple, I guess, this example I'm giving, we can write it in the propositional logic, and we can say like P, which is a fact, I love you, and not P, I don't want to say it because I love you. So it's P, because Jeremy is always finding my wrong examples. But let's go to another example, which is related with this breeze and pit. So we cannot say pits cause breezes in adjacent squares, for example. This is very complicated to express in the propositional logic. So we can write it, however, in like, but in different like pieces, but it will make the problem more complex. Okay, so this will, let's say, put an end for now to the propositional logic, but still useful, still like we are like until today using propositional logic, but we further, if you remember that timeline, we move from one logic to another. Why? For which reason we keep moving from one logic to the other?
Go to the real world.
You are right. So we are approaching the reality, and the reality is having high, like could be represented with high dimensions. High dimensions means like more near to the natural language. Means I can say anything I want, like pits cause breeze in adjacent squares or whatever. So we are going now to quickly go through the first order logic, and here it's like combining the best of formal and natural languages. Here, so when we look at the syntax of natural language, the most obvious elements are nouns, pronouns. This is what we were discussing right now. But there are verbs and verb phrases that refer to the relationship among objects. Like I was saying, I love you. The I and you, it's important as well. So how to do or how to approach this? So in order to go through the first order logic, we have propositional logic only assumes the word contains facts. I love you, this is a fact. But if we will move further, the first order logic, like natural language, assumes the word contains objects. It's you, it's I, it's people, houses, numbers, or whatever. Relationships between these, for example, around, prime, I don't know, so whatever verbs that could be used, and functions. Function, I love you because you are my students, I'm your teacher, I love you. So in here function, it means the relationship that is between two objects, let's say. So we will go to an example, which is from the very, very, very old time. In 1189, yep. So here in England, I don't know if you have seen this example or not before. The example of two brothers, Richard and John. Okay, so this example is where we started, like about probability things, which was explored and, or let's say, model, like represented, let's say. So here what we have Richard, which is the king of England. He has his brother, okay? His younger brother is called John. Now, if Richard is the king, we can assume that he is a kind person, he's a responsible one, he has that qualities of a king, okay? And now his brother, he's like, let's say, the evil king. So he's not kind, he's not good, let's say, and he's not good, okay? So how to represent this relationship between these two brothers? So this is already existing. So this is just a representation that has been introduced not only years or decades, it's a long time ago. So we are going through it just for seeing how this first order logic could be represented. So here, what we see in the image, we see that the representation of these two guys is given by, first of all, them. So here, this is R for Richard, this is G for Joe. So each one is having as a representation an object, which is his left leg. While the left leg here, it's a sign, or it gives you an idea about it's going in the right path or in the wrong path. So we can expect, so Richard is the person who is going on the right path, is doing good and so on. And John is completely the opposite. So what is the relationship between these two guys? So it is Richard is the brother of John and vice versa. So John is the brother of Richard. So the relationship here is a brotherhood, and we mentioned or presented as a like list, Richard and John, or John and Richard. So it's from both sides. As we can see here, we have the arrow is going in both directions. So on here, the relation here, on here, the relation here, where there is nothing, and here there is the crown. The crown is supposed to be for Richard, but let's say John is like wants to take. So this is how to present that, because it will be like a long fight and a long story, and it's all about the crown, okay? And the functions now we have the left leg of Richard, and the Richard's left leg of John, and so on, okay? So to represent this, now if we want to present this in the propositional logic, this much details and this much like things that could be described even as a storytelling with a natural language, so it represents the fact as it is. It cannot be only presented through the propositional logic. So here we need more like elements. We need to represent thanks to constants. Our constants in this case are John and Richard and so on. Variables, we can denote by X, Y, or A variable that may take different values. It could take, if I have only John, that is a constant. If I have only Richard, that is a constant. But if I say X could be John or Richard, so it's a variable that may take different values. I have my predicates, which are the relations here, brother or someone is superior or inferior or whatever. The functions here, functions that are represented in this problem are within the left leg of, okay? And the connectives, we have the typical connectives that we went through in the propositional logic, the not, and, or, implies, and biconditional. The equality, so here we have it's equal or not equal, and also we introduce the very important thing, which is quantifiers. Quantifiers like exists and for all, in order to generate, okay? Is that clear? Okay, yep. That's great. Now, we are going to have some examples. Just 1 second. Okay. This was expected to be a quiz, but let's do it together, okay? Let's be honest, we don't see this. So, if we have an atomic sentence, it means that we have the predicate, and in parentheses, we have the set of terms that are there. We could have the term which is equal to the other term, and here we have the term is a function, as function of the different terms, or constant variable. So if you want to say that, or I will not ask you, so you are going to tell me which this like sentence written in the first order logic means in the normal language. So the first one, the easiest one, says
John and Richard are brothers?
Yes. So John is the brother of Richard. So here the order is important, because as we seen in the previous example, if I want to illustrate the arrow going in both directions, I need to say brotherhood Richard and John, and also John and Richard. Okay, so here we are just expressing this from John to Richard. Okay, now this one,
The father of Richard and the mother of John are married?
Yep. Okay, next.
The length of the left leg of Richard is longer than the length of the left leg of John.
Yep. Is that clear? So this is just how to write things. It's like encoding the real world, okay? So we start learning this, and then we have, these are simple or atomic sentences Now for more complex sentences, here we are not using that connectives that we see in the and or the not or the or the bidirectional implies. So for more complex sentences that are made from atomic sentences using the connectives, let's read this together. Yes?
The left leg of Richard. It's
Mhm.
not the brother of John.
Farah?
The left leg of Richard is not the brother of John.
Okay. And here, the left leg of Richard, it's supposed to return what? It's a function.
Yeah.
And the output of this function is what?
Mm.
A value.
Right.
So this value is different, okay?
Mhm.
They don't have the same value of the function left leg of. Okay, and next,
Richard and John are brothers, and John and Richard are brothers.
yeah, this is what we mean with the brotherhood relation in the start. Next,
Richard or King John.
what?
Richard is the king or John is the king.
Or, yes,
Either one.
yes,
Like,
you're right. And the last one?
If Richard is the oh, sorry, go ahead.
John is the king. That means that John.
Yep.
Richard is not the king.
Implies
That means that John is the king.
or.
Or
If
if
Richard is not the king, then John is the king. Okay. Is that clear?
Yes.
Okay. Next, we have the quantifiers we were previously introducing to. The universal one, which is like for all, every president is smart. We can like illustrate this in the first order logic, which is for all x president of x implies smart of x, okay? And existential quantifications means exists, there exists x president x, and at the same time, this x president x that exists is smart, okay? So these are two quantifiers. And now I will let you with this like quiz. You can do that. So we are at week 4. I will publish everything. Yep. So week 4 is now supposed to show up. And what you will do is we will start with the first quiz one. You will find it at the end. What is it? Expressing.
coin.
Oh, no.
Well,
Okay, this one also we can do together. We have more quizzes to do online. Excuse me. So this one we can do together as well. So John has 2 brothers, Mark and David. You can take your time. Yeah. And it's good sometimes to have one pen and paper and try to write your thoughts and what you think. So try to think of it. If you want, I give you 2 minutes. And then we can go through the correct one. We can go through these examples one by one. Okay, so the first one, John has two brothers, Mark and David. What is the relationship?
Brother.
And who are our constants here?
John.
Mark, and David.
Okay. Oops. Okay. So John is having two brothers. The first one is Mark, and the second one is David. So Mark is the brother of John, brother John Mark, and David is also the brother of John. So brother John David. Is this clear? Okay. It only says Mark and David are John's brothers. We need to make sure John has no other brothers. So what we were mentioning in the start, that was said, but we need an additional information that there is no more brothers. Here, if we see like words like other it represents what?
All other very
All other potentially existing brothers. Okay, so here we have the quantifier all. This is what we will need in this sentence. So yes, I'm helping. So first part is done, second part is done, third part we have the for all x brother John x. Then
X and A, only Mark and David.
you are right. This or this. So the implication is in between these two relationships. And the last one, John might have only one brother with two names. So,
X is the name.
the names are what are the names of the brothers that could be based on this example? Sentences
Mark.
are- yeah.
Mark
David
or
and
David.
Yes. So our variable is x, and x is going to take whether the value David, Or-
Mark.
which is different from David.
Yeah.
It cannot be David and David. Okay? So this is an example of how to write that. Is that clear online?
Yeah, I followed almost all of it, but if I didn't chain the brother John Mark and brother John David with my second two. I just sort of put, and I didn't do the for all x either. So my second one was just your second line there, brother John x implies x equals Mark or x equals David. Is the top line still necessary if we're going to put these
Yes.
together?
Yes. Yes.
Okay.
Here, if you can see, we started like from the very basic idea we want to illustrate or represent, which is the brotherhood between John and we don't care who else. The start we said they has two brothers. Then we said the names of these brothers, and still in the last sentence, in the same logic, that John is having brothers. Okay, so we need to illustrate this, and we will check the names, which is the second evidence. Okay.
Okay, so for instance, if I just put that second line in there, it would really be kind of like saying, if John has a brother, they are going to be named Mark or David, or they will be one of those people, but it doesn't actually say that they're brothers.
I just want to confirm, Jeremy, are you mentioning the x is equal to David and then Mark is different from David? This
I wish I
part
could-
you are-
I wish I could show you, but I don't think if I hold this up, it's gonna
No.
work.
If you are
Um,
mentioning that Mark is different from David,
No,
here
I'm
it's-
still on the second one, but I only put the second line. So brother John X implies X equals Mark or X equals David. That was the whole thing I had for my second one. I'm trying to figure out what that would actually mean. And the only thing I can think of is if John had a brother, it would turn out that they are named Mark or they are named David, but it doesn't actually say that he has a brother if I just have that line.
Mhm. So for the second one,
Mhm.
still with the same thinking, we need to illustrate the idea of brotherhood between both. Like who is mentioning in the start? This is our logic. If we remove like this like set of we treat it separately, maybe we could have different results. But if I have it's like I'm storing information, and none of the coming information is going to contradict with the previous one. So in the start, he's having two brothers, Mark and John. Next, it only says that Mark and David are John's brothers, and we need to make sure that there is no other brothers. So still we need to confirm that he has a brother called Mark and a brother called John. So we need, first of all, to have this relationship exist given the first part. And next, we are going to check the whole world. We are going to see the omega universe, taking which possible values. So from these values that X variable could take, we just need to make this, like, to double check that there is no one else. But in the start, we always need to prove this brotherhood relationship, because if you remove that, we don't mention that brother John Mark and brother John David. Here it's like we are showing the arrows going from the node John, one going to Mark and the other is going to David. So like this, we are confirming 100% sure about this relationship. If we don't do this now, you eliminate this, you will only consider for all X brother John X implies X is Mark or X is David. So here it's not only talking about the specific relationship between the given John that we are studying and his two brothers, Mark and David. It could take any X, any relationship, any constants. But in the first part, we are putting the constants that are together in the real given sentence. Means we need to illustrate that as well.
Okay, that
Is
makes
that
sense.
clear?
Yes,
Okay.
thanks.
Thank you. So we move now to more fun with the first order logics. So brothers are siblings. So when we have something which is in some term, we are not in the previous case, we say Mark and David, we are specifying something. We have our exact constant, and the constant takes exact name, as I was mentioning before in the table. Now we are talking about variables. So whoever brothers, and how many brothers could we have? It's an omega word. So what we have, it's for all. And to illustrate brothers, it's a relationship between two. We have one and the other brother. We fix one and we can keep checking, okay? But for now, brother is a relationship between X and Y. So if for any or for all X and Y brothers, relationship brother X and Y implies they are siblings. So we are introducing a new relationship. So if we have the first one, the brotherhood relationship, it will take us to the siblings relationship. Next, now, sibling is symmetric. In order to illustrate something which is symmetric, it's going in both directions. If, for example, sibling of X and Y means Y is also the sibling of X. So here we have the bi-directional. Again, we are addressing the whole world. It's for everyone, for all. So for all XY siblings, XY, it's like bidirectional sibling YX. One's mother is one's female parent. Think of it. Again, how to justify the use of having for all. If I'm not talking about the exact mother of Ayub, for example, the exact mother of Farah. I'm talking about the general. If I'm not having exact constant, then I'm going to illustrate with the quantifier for all. And here, the relationship now, there is two relationships or three. Mother, female, parent. So mother, it relates to variable X and Y. And this X, if it is female, it will return true or false. And also we have the relationship parent XY. So we can write that as for all XY mother XY, it's biconditional, female X and at the same time parent XY. Is that clear? in the start, it may seem like Chinese if we don't like discuss it together and start to learning that. But if we will be familiar with that, probably if I give you a given sentence, you will be trying to write it in this, let me say, language or expression. Okay, given this logic. So a first cousin is a child of a parent sibling. First cousin, it's a relationship between X and Y. For everyone, we are still talking in general. We don't have a specific example or constant that we are dealing with. And a first cousin is a child of a parent sibling. Here, somehow, I am confirming something that if I have something, then there exists a result of that, for example. It's biconditional. So here we use the exist because it's not for all. Okay, so exists P, PS parent PX, and siblings PS and P, and parent PS and Y. Think of it. If all okay, then let's move. So red is here. We have no one in the waiting list. Okay. Yeah. Is that okay?
Yeah.
Great. So now what we have? We have examples of the assertions, and examples of the queries and goals. So here what we have, again, sentences are added to the knowledge base using tell, how we are going to store things or to add to the knowledge base. So if I want to add things, I will put that like sentence written in my first order logic, and I will add tell. It's like add to the knowledge base. For the queries, we interact by asking. I would ask this, and it will return me like true or false or a given number. For example, if I want to ask about the previous example, the function that we have was left hand, left leg, something like this. Yeah, left leg of Richard, for example. It could return true or false. For example, if I'm giving as input Richard and it's John, or John and it's Richard. Or in the last example of atomic sentences, we have the superior. It could, it must, in this case, for example, return a given value. For example, he is 1 meter, or I don't know what, how much is the length of that particular case. So finally, we are done with the first part, which is the logic, first order logic and propositional logic. Still, we went through the, the timeline, and we were seeing that there are more logics, and each time we are introducing like linguistic variables. These linguistic variables are used mainly in order to approach the representation of the real world. And the last one that we have seen that is in this timeline was the fuzzy logic. So for the fuzzy logic here, we were discussing with Zoya. She's going to prepare a presentation. So most probably we are going to have that presentation next week with the same class with the review for the exam, okay? Because so we will give like 30 minutes, 45 minutes to the presentation and discussion, even less. And then we will go with the review. If you have any questions or something, we can discuss that. So for the review, I am going to prepare for you an example, which is maybe similar to the exam. So it will help you to prepare for the exam, which is not going to be difficult, as you are having access to use open source for this case. However, I know very well that if you're having access to the net, to the slides or whatever, because I was not planning like that, but as we have asynchronous exam, so I'm sure that it can happen. For having equal opportunities for everyone will be having open access, and it's not my main goal to make you fail or something. So I will be happy if you're going to have good results, but also to be faithful, I'm going to have that final project that is going to give for everyone, like whatever, if he's really getting the AI project and he's understanding the basic concepts, he's doing efforts or not. So don't worry about the evaluation. And let's move to the next part of our knowledge representation and uncertainty modeling. So we were talking about uncertainty that logics are or may be used for modeling. And now I may take you to, we are approaching the fuzzy logics, by the way, because as we were mentioning last time, and Zoya, maybe now she's having like enough knowledge to say that fuzzy logic is when we are not talking about the binary facts, if a fact is true or false, or proposition is yes or no. So if we are having the binary like case, like black or white, we don't talk about the gray. We don't have degrees of like belonging to some interval. In case we are going to discuss with degrees of belonging, like I always given the example, it's cold in this like classroom, 70% cold, it's not cold. However, there is 30% that it's hot, okay? So if we translate these given values, it says that 0.7 is a probability that this room is cold, at the same time that we know that 4 possible values are cold or hot. And the sum of probabilities is equal to 1, which means or translates to of a probability of 0.3 or 0.3 for cold or hot. Oh, yes. So you're concentrated. That's good. Is the idea clear? Okay. So now we cannot do AI, and we could do, because maybe you can check some other AI classes where straight they dive into machine learning, they dive into deep learning, they dive into reinforcement learning and more advanced topics. However, in this class, I am doing my best to not make it boring, but I see it extremely needed and fundamental for an AI experts like you to have the knowledge about probabilities, about basics, and mathematical like background. Maybe some of you are having this mathematical background, so what we will do that we are going to refresh this memory. For others, you may not have, so I am presenting the key concepts that may help you through the AI class. So one of the very important points is the Bayesian networks. And these Bayesian networks could be also seen as in a more advanced like stage. And another variant of them is the Bayesian networks over time. So we will focus for this week on these 2 points. And then, so we will be really starting the machine learning, deep learning to see concrete applications of AI. So what we mean by, so we were talking about probabilities, but let's come back to this example of maze. So our main goal was that our agent was in this starting point, in the green point, initial state we call it. And from this initial state, and given this maze where we see that these black walls he cannot cross, we have our goal test. So each time we see some algorithm that is going to take us to this goal, and these algorithms were seen like it's a rule, it's a given steps. So like, for example, Jeremy last time was saying that I'm trying to implement one of the algorithms, for example. So he knows exactly what is the algorithm, and for each algorithm, he is supposed to know what are exact steps that I may take. And I'm sure that if I give the same algorithm for 2 people, we must come up with the same path towards our final node. I was mentioning that, okay, these are the existing algorithms in the state of the art. However, we could like mix, we could use some like evaluation functions, we could add some optimization part. But what we did is just we were going through the general algorithms like the DFS, the BFS, the A-star, the min-max, and so on. Now, let's come back. If I have a given algorithm, I could solve this like maze. But in addition to that, if me, for example, I have an additional information that this maze is not taken in the normal conditions. I know that there is a new variable now appearing, which is the wind. I have information about that AI navigating this maze could be doing this, trying to solve in a windy day, for example, or not. If yes, for example, let's say it's the probability that the wind is pushing him towards the north is 0.8, for example. So this will change the way or the path that is taken towards the solution. Here we understand that it's not always black and white. There are some conditions sometimes that may impact. And here we are introducing probability. When we talk about probability, we have its unlimited space, let me say. Now let's take one example. Let's say that your car is not starting today. It's not working. I wish it not happen. Yep. But let's say if your car is not working and you are the expert of cars, not like me. So what you will be starting asking yourself, what is the reason that my car is not working? So you may think different reason with different probability values. So you may think my battery is flat. It's possible. It may be because there is no oil. You need to do oil change or to check or whatever. Or there is no gas. Or the fuel line is blocked. Or the starter itself is broken. If, for example, the battery is now flat, we have taken a given scenario and it is why, ask me why. So this is, don't ask me why, this is ask me why. So ask me why the battery could be flat. Maybe because it's dead. Maybe it's not charging. You understand? So if it's not charging now, so my car won't start because of my battery is flat. And the battery is flat because the battery is not charging. And maybe that is because the alternator is broken. Or maybe because the fan belt is broken. So here what we can see that there is unlimited possibilities, and from each possibility we can go to another one. Here there is a what we call dependency. It's kind of the not charging may depend whether from this condition or from this condition. Okay, are you remembering, or it means something for you?
Makes sense so far.
Yeah, so just to know, is there anyone with us in person or online that didn't take any probability classes?
I mean,
Sort of.
yeah, specifically probability classes, not really, but you know, I've taken enough math that it's just percentages.
Yep.
Yeah, same with me. I took statistics and business related probability.
Okay. Then sometimes you will find me coming back to the basic things. I'm putting backup slides for that, so that's great. Now what we have, this is another example, and I remember this example we seen last time. So the example of the alarm. So there is an alarm that could be due to two factors, whether there is a burglary or there is an earthquake, one of them. It's really one alarm, like in your house, you're putting one alarm, only in case some thief is coming, or for this is the main reason, okay? The beep is the main reason. But it can happen that when there is an earthquake, the alarm is going to work, but it's not the real reason, okay? But there is a probability. Now, suppose you have two neighbors, one is called Mary and the other one is John. Now, if you're having an alarm, the voice of the alarm, okay, that also can make you think that Mary is calling, and let's suppose that Mary is always making parties and is always having a big mess in her house, and even if you are calling Mary, Mary, she maybe cannot attend. And if you are calling now to John, maybe John will think that it's alarm in his phone or something. So it's a set of connected events. If I take only the example of one alarm installed in my house, for example, and there is infinite possibilities. So we are going quickly through this example to illustrate that if I have a fact, we are not that is true or false, like before in the propositional logic. That is true or false means the probability value is 1 or 0. Now we have the probability value could vary such that if I have two elements that could cause one fact, my alarm is there, whether because of a burglary or because of an earthquake. From this, I could say that the sum of probabilities of these two elements is equal to 1. This is I know. This is I'm 100% sure. Okay, there is no other reason up to this representation. Is that clear, guys? So the idea of probability is clear for you?
Yep.
Okay.
Yep, makes sense to me.
Yep. So if we are talking about probability, we are talking about uncertainty. Means we are not sure if it's an earthquake, if it's a thief, if so. I'm introducing this. Now, if we are talking about probability, if you have taken probability class, you must remember 3 like concepts in probability. The first one is the unconditional probability. When we say unconditional, means there is no relationship between two elements, let me say. Okay, so here the degree of belief in a proposition in the absence of any other evidence. I won't care about anything. This element is independent from any other element that could exist. The conditional probability now is the opposite of the unconditional. Now I have a condition. So it's the degree of belief in a proposition given some evidence that has already been revealed. So something is happening. For example, my students are sending me lots of emails. This is a fact. So I am happy because this explains that my students are interested in my class, for example. So if next time I am going to teach and I will not be receiving emails. So I think this is an important condition to let me know or to guess if the students are interested or not. So if I have lots of email, it shows the interest. If I don't have, means my students are not interested. So this is an example of conditional probability, and we denote that by P, to say probability of A, which is the fact, such that, or given the event B is happening. So this is P of A given B, which is the conditional probability. So my condition in this case is B. Is that clear? Okay. Now we take some examples, like for example, what is the probability of raining today, given that the information about raining yesterday, it was raining yesterday, for example. Or I can ask, given the information about traffic condition, is there, for example, any changes in the route or not? I can also, in the medical context, I can ask, given the test results, what is the probability of having or not a given disease? Okay, so this set of examples, or we need to have some formula to illustrate that. So we were just coming from the propositional logic, and now we are talking about the probability of A given B. Given B means I know the value of the probability of B. So B is known. This is why you will always find in this side the division by B. Okay. So what is what are we going to have here? So given B means B is already there. Now what we need to know, it's A and B. So the probability of A given B is equal to the probability of A and B happening together divided by the information that we may have, that the probability of B to happen. Is that clear? Online?
Yeah, makes sense.
Okay.
So you always
Just-
have to be given at least one, right, to be able to understand the syllogism? Okay.
Yeah. So only for your, like, I know that probability classes may be boring, and I'm doing my best to not feel that. But just to let you know that why I chosen to put this part, to include it in the course, because I went before through like interviews in industry. Most of you maybe they won't like finish with a PhD, or so whenever you are in an interview for AI position, make sure that you will be asked for questions like about Bayes rule, about the probability, the conditional probability, and you may have even like kind of multiple choice thing to prove that you know all this. This is why we need to understand it, to really observe this. So observe it. So if I have the probability of A given B, 100%, I know about B, so I'm going to divide by B. There is a relationship A given B means A is happening and B is happening, so I need to like use the probability of A and B. Is that clear? So just please try to memorize right now. If you don't, we understand together to keep in mind. So we have this probability of B given A is equal to the probability of A and B divided by the probability of B. In this case, what we can do, or we can write this in different way, if I am going to multiply in both sides with the probability of B this way, it's going to eliminate this one, and the probability of B this way. So what I will be having? I will be having the probability of B multiplied or times the probability of A given B is equal to this entity, which is the probability of A and B. So given a rule, you need to learn that. You can like come up with the, if for example, you need to know the information about probability of A and B. So in this case, you must have A given B and B. You understand? So if, for example, you need to have probability of B, you can divide these two. So each time it's like a puzzle, and you need to know what you have and what you need to compute. Okay? Now we have the probability of A and B is equal to the probability of A times the probability of B given A, which means that I have A and B. I can whether use the B, and I know that B is given, or I can use A, and A must be given in this case. Okay? So all these are like derived from the same equation. And now let's move to the next concept, which is the random variable, which is a variable, as it's mentioned in the name, is random. So we have like a domain of given values for each like variable, and we don't know which exact value this random variable is taking, so we call that a random variable. Let me say X, for example. So X could be a random value, it could take any given values. Now, for example, now we consider a given problem and we try to check which are the random values. So we are limiting the space. Now I am going to roll a dice, and I know that the dice is having 6 faces and from 1 to 6. So my random variables that I could get in this case are numbers from 1 to 6. If I have the example of the weather, I know the different values that my random variable weather could take: sun, cold, cloud, rain, wind, or snow. Also for traffic, there could be traffic, no traffic, or light traffic, or heavy traffic. So my random value is the traffic, and these are the different values that it could take. If I'm going to throw one coin, it could be having whether the head or the tail side. So we will be checking this element and this example later in the quiz. We also have for flight, for example, it's on time, delayed, or cancelled. And let's take an example. So we have a random variable. Our random variable is flight. It's taking 3, 4, 5, 6, 7, whatever the number of possible like values that it could take. The most important for me is that the sum of all these values is equal to 1. So for the case of flight, let's consider most of the time it's on time. So it's the highest probability value, for example, 0.6. And if it's delayed, it's 0.3. If it's cancelled, it's very rare to happen, so it's 0.1. In this case, we have the probability distribution, and the sum is equal to 1. So we represent that given this like list, which is, for example, we were saying first element on time, then delayed, then cancelled. We just mention the values in the same order, okay? So independence, now the knowledge that one event occurs that does not affect the probability of the other event. Now, if, for example, give me example of 2 events that are independent.
Student coming to the class and the weather.
Yeah, so it's raining and it could be independent. It's based on our understanding. If I will like connect them if Farah is coming to the class and it's raining, because Farah is a hardworking person. So whenever it's raining, I would expect Farah to come, and maybe I would expect some elements not to come. Somehow,
But logically, if it's snowy,
Yeah.
impulse won't come. Or you
yeah. So this is discussion. It means what? It means now what we are discovering or exploring random variables. So it's up to us to say these variables are dependent or independent. So in maths or in general, we are representing a problem, and that problems would tell you if these variables are dependent or independent. Otherwise, we could give an example and we get a counter example that these are not dependent, okay? But things that cannot happen at the same time. I'm teaching you and I am sleeping already. So it cannot happen, okay? But I may sleep straight after the class, for example. Okay, is that clear?
Yep.
Online,
Yes.
great.
Yeah,
Makes sense to me.
Great. So I'm happy to hear that all the time. Now, independence is illustrated by probability of A and B is equal to the probability of A times the probability of B given A. So we went through this. Now, if both elements are independent, means I am computing. I know this. I know that the probability of A and B together is the probability of A and B given A, okay, times. So here we know that A and B are independent. If things are independent, means how to consider the probability of B given A? It's the same as probability of B because A won't have any impact on this value. So in the case we have independent like variables, we just can write that as probability of A times the probability of B. Now we have this example. You are supposed to take 5 minutes rest, okay? So you will take 5 minutes quiz. So I will really give 5 minutes. I'm sure it will be done before. So the coin flips example is available in Canvas. So try to start with the first quiz. Now in this example, we have coin flips. If we have a given coin, one side represents the heads and the other side represents the tails. Now, we need to check each time the probability. If I have my head coming with a probability of 0, 5, what is the probability to have tail? Then you will deduct this, but you have the rule for deducting this t value. Then if I have, now, what is the probability to have t and after that h? Coming means I'm going to throw, the first time I will obtain 1 t and the next time I'm going to obtain 1 h. And then what is the probability to obtain 3 times sequential t, then t, then t. So I will obtain the tail 3 successive times. Again, so if we switch or change the value of h from 0.5 to 0.4, we check the value of t, we check t, then h, and then we check the probability of having a sequence that is having t followed by another t and ending up with an h. So you will find the answers. Oopsie. Okay.
A2 is the probability of T is known that we have tails.
Sure. It's known that we will have what we have in black. It's that what we know. From that, you need to deduct or to extract the rest of probabilities. And please, I'm mentioning I think in the homework, I don't have that in the slides. If sometimes it will result multiplication like we've seen before. So if you will multiply, just write for me, for example, P1, which is a given value, for example, 0.5, multiplied, which is the star sign in the keyword, without any spaces, and equal without any spaces the result.
So comma is and or and?
And, yeah.
Okay.
T and T and T, which is equal to a sequence of T's. And, yeah.
What's the probability to get 3 t?
Yeah. And I remember, by the way, just to let you know, one of the interviews that I had in Dubai, it was a good company, I was asked to answer like this. So always remember that whenever you have comma in AI or in probability, that translates with an and, logical and. And if we have an and, you need to check if your variables are dependent or independent. In the case of independent variables, and like you know the previous value, the probability of each of them, so you are going to just multiply elements, okay? So probability of A and B is equal to the probability of A multiplied by the probability of B.
I didn't know if we must find the probability of H given T or the probability of T.
It's not given. Here we don't talk about conditional probability. We talk about and. I want to find in the start a probability of T. I have some information, so I know the sum of probabilities is equal to 1. Next, now I have a T.
Okay.
Having a T with this probability, how could I have this T and next H? So you already have the probability of H and you are calculating the probability of T, and the and is like a multiplication, okay? Because they are independent. So I think I solved this. It's done. Now I will be quick if I'm already giving the answer, so I will be quick.
Excuse me, Professor.
Yeah.
I finished. I had a couple spaces in mine, accidentally.
Oh, it's because of spaces then. I was expecting this, and this is why I was mentioning you need to be careful with no spaces. Okay.
Yeah, it was spaces right at the end, and I didn't even notice them.
Okay, so I will note that. So, let's check. Understand why they ask these questions in an interview? They are not wrong to ask. The very simple things is extremely tricky for 100% of people. And myself, when I was taking the AI class, I've never paid attention to these things. But you can believe me that this really has been asked in an interview, and this is why I'm saying I need to mention this very well, and I need also to put it as a quiz. So even you are getting bad results, it won't impact, because in my class you are going always to have extra points and it's going to fix things. Whatever mistake you are doing, whether you're making extra spaces, you are like solving it wrong, don't worry, there will be extra points at the end. But I want you really to understand how serious is this. Yes.
We have to put the equal at the result. Just put the.
Ah, okay then.
That's why.
Okay, in all cases, I hope the result also reflecting that we need to be very careful about this. But I'm giving already the format, and there will be more exercises like this. So always, let's take an example. I have h is equal to 0.5, means t is equal to probability of having t is equal 0.5, because the sum of both probabilities must be equal to 1. Next, now I have this is equal 0.5, 0.5, it's 1. So the probability of having t is equal to 0.5. Then I must have and h, which is 0.5. Then I need to write 0.5 multiplied by 0.5 equal to 0.25. Okay? It must be the syntax. So, okay, for this quiz, it would be like not impacting, but now on, whenever there will be a quiz about probabilities, no spaces, just you mention your formula equal the result. Now having 3t, as like I have t is the probability of 0.5, so 0.5, 0.5, 0.5, which is 0.125. Then I have now, in this case, what we call it? It's equal probabilities for both of possibilities. Now we have more probable, it's more probable to have a head than having a tail, or it's the opposite, a tail than a head. The head is with 0.4, means the tail is with probability of 0.6, which is 1 minus 0.4, okay? Now having t and then h, I would like multiply the probability of t, which is already 0.6 by 0.4 to have 0.24. Now if I want t and h, I would have 0.6 multiplied by 0.6 multiplied by 0.4, which is equal to 0.144. Is that clear for everyone, please? Okay. So these are just notations that given a random variable x and y, we have the idea of complementary probabilities, which is if I have the probability of not having x, it's 1 minus the probability of having x, and the independence relationship. So please focus with the symbol for writing independence. It's like this. So we have x is independent from y, means that the probability of having x and y is the multiplication of both probabilities, p of x multiplied by p of y. So this is I say p of x or p of my big X, which is the random variable, is equal to the little x. It's the same notation, okay? It's just notation. Now let's take this example. And so I may give you time for these examples. So I think, so I will be sharing with you the, the slides without answers, and you have the quizzes. So it would be like your homework to go through these different examples that I am mentioning, just to practice, because it's extremely important. So we have as the example of the coin like flipping here. This is another quiz that we will be having separately. And then what we will have, we'll be introducing the Bayesian rule. Quickly now, I will try to go through this like Bayesian rule and keep you practicing alone. But this Bayes rule, it says that the probability of A and B is equal to the probability of B multiplied by the probability of A given B. And here, so it's the same. If we are going just to switch the variable. So I don't know about the probability of B. I have information about the probability of A. So I will be having a probability of A multiplied by the probability of B given A. So this will take us to, if I have two elements that are equal to the same elements. So from here we can deduct that these two elements are also equal. So the probability of B multiplied by the probability of A given B is equal to the probability of A multiplied by the probability of B given A. So in the start, we were introducing concepts about probability. The most important, maybe now we see the conditional that we can visualize here, and the independence as well, or the dependence between variables. These concepts are key concepts. Now we have these rules, they are now separate. We were writing this and it's clear now for everyone. From this, we are trying to deduct some rule. Keep like this in your mind when someone will ask you after like 1-2 years about Bayes rule. You remember what I know about probability. Probability given a condition. So the probability of A given B, it's could be written in 2 ways, whether I have information about A or I have the information about B. In all cases, I will multiply with the probability of whatever I know given the other element. These are equal, and if I will put this in the same like equation, what can I conclude? I can conclude, that the probability of B given A is equal to the probability of B multiplied by the probability of A given B divided by the probability of A. And this is the Bayesian rule. So if I do the opposite, so I can also have the opposite. So here I'm giving an example, application of the Bayesian rule. You are going to have that as a homework as well. And try to predict, or if I may share this one with you, it's a direct application of the previous equation. If, for example, I know very well, given it's cloudy this morning, and so what is the probability of rain in the afternoon? I know that it's 80% of rainy afternoons start with cloudy mornings. So I have data about what happens in the past 1 year, 2 years, or whatever, but the conclusion is that 80% of the cases, when there is a rainy afternoon, it means it's a cloudy morning starts with a previous rainy afternoon. Sorry, before the 80% of rainy afternoons start with cloudy mornings, yeah. I have 40% like probability of 0.4 of days have cloudy mornings. I have 10% of days have rainy afternoons. These are the like facts that I know. I'm going to apply the rule and check what is the probability that it rains given clouds. So it's the probability of clouds given rain multiplied by the probability of rain divided by the probability of clouds. And I have these different values, and it's like 0.2. So how to decide which formula you have? It always depends on the values or probabilities that are given to you, okay? So next, now what we have here. So these are examples, like for example, knowing the probability of cloudy morning given a rainy afternoon can help me calculate the probability of a rainy afternoon given like cloudy morning opposite. The same for the case given I have, for example, the probability visible effect given unknown cause can let me conclude the probability of unknown cause given visible effects, and so on. So this example also I am like now is published in the Canvas. It's going to be a homework. There is nothing to do with that assignment. You are just going to watch this video. If you are seeing this video, you are going to get your like graded well. So this video, just quickly, it explains or illustrates the idea of Bayes rule. I found it really like it's a very nice video, and you will understand that after watching. So you need to watch that to understand. So given an element, what is the probability if this person, like if we have people and we randomly like take one person, what is the probability of this person to be librarian or a farmer? So this is the concept. It's really well illustrated in the video, so I encourage you to watch that. And next, so I am keeping you with the reading part of this problem that we will be discussing next time. It's just like still we have 2 minutes. So it's the idea of a TV show. So in this TV show, we have the 3 doors, and the person like presenting this show is giving to his guest these 3 doors. By himself, he opened 1 door. There are 3 possible things: whether he will be winning a car, this like guest, whether there will be a goat, or there is nothing. So me, let's suppose I'm inviting you. I'm going to open the door. I will check. If, for example, I see 1 goat, for example, I will ask you, I'm seeing this, are you willing to switch between the 2 probability that you may have. Means one is empty door, one is a car. You want to switch or you want to keep your life decision. So how this problem has been solved is an interesting story as well. It's a real world story. So I want you to go through this. Just read it. Try to, it's just for your like general like knowledge. And then, so this is just an example. And so introducing the Bayesian rule that we were already discussing. So plenty of examples I'm mentioning, and next time, so we will be moving to the Bayesian networks, okay? But before that, I want to see you like mastering really well whatever basic concepts we were going through and the Bayesian rule, okay? Okay, any questions online?
No.
No questions?
No.
Okay. So see you next time.